Hello, everyone. We are back and we are about to get into Lecture 7, which is looking at total uncertainty, bias error, and propagation of error. So let's go ahead, and we have been basically focusing exclusively on precision error thus far in the course. So we've done t-tests, we've done p-values, all of these all of these excellent statistical tools, chi-squared, goodness of fit test, but we forgot that our total uncertainty in some measure and x is equal to the bias error squared plus the precision error squared in x. So we've just completely neglected that this is actually our true 95% confidence interval where we're going to actually plot our total uncertainty u of x. So that's an issue. We are going to actually start to account for that today. And more importantly, how do we deal with problems like the following here? So if I want to measure the volume of a cylinder, we know that the volume of a cylinder is pi times r squared times L. R is the radius of the circle, L is the length of the cylinder. When you're thinking of uncertainty, I want the uncertainty in volume, but there's going to be some uncertainty in my R measurement and some uncertainty in my L measurement. Not only in the precision in R and the precision in L, but there's going to be some potentially bias in R and bias in L as well. So we're going to have to figure out how do we actually incorporate all of those bias and precision errors. Well, one of the things that we're going to have to do is propagate our uncertainty. And this is particularly of particular importance for our bias error. So when we measure several quantities and we want to calculate some desired quantity, and each measurement has some associated uncertainty. We're going to they're going to create uncertainty in the calculated result. So we have to propagate that uncertainty. So there's a well-known statistical theorem that if I have a linear function y, so a function y of some variables x1, x2, x3, and each of those variables has some standard deviation, uncertainty, I could calculate that standard deviation with the following formula. And this is of critical importance here, so let's zoom in a little bit. So I'm going to take the partial derivative of this function y with respect to each variable multiplied by its own standard deviation or uncertainty. Now, you can actually utilize a first order Taylor expansion, and instead of having this standard deviation, we can call or invoke some uncertainty in the variable x1, x2, x3. So if I want the total uncertainty of a linear function y, I can simply do this, where u of I is going to be our true bias uncertainty in that variable 1. So for example, we've done problems and questions where we're looking at if we're measuring with a ruler, that ruler has tick marks of plus or minus. Basically, you could resolve plus or minus a centimeter. So you can plug in that uncertainty here. So they need to be independent of each other and have the same odds. And they must have, essentially, we're going to be operating at that same confidence interval. So that is kind of the key to this analysis. So let's go ahead and next time in the next video, let's do an example and let's hammer this home. So see you then.